Okay, it's a little after 11 a.m. here in California. We're going to go ahead and get this thing started. My name is Vince, and I just want to welcome you all to this presentation of the best webinar series brought to you by Novedge, Design Software Superstore. I want to thank all of you for joining us today. We're excited not only to present 3D pattern modeling with ParaCloud Modeler, but to have Eyal Nir presenting it for us. Just a little background on Eyal. He's an architect and IT specialist with over 12 years of experience. He received his BA architecture degree in 1999 from the Technion in Israel. He later worked with Foster and Partners, specializing model group on various design icons, as well as forming his own architectural practice. Upon completing his PhD in 2005 at the Technion, he founded ParaCloud, a software boutique for generative modeling tools. ParaCloud GEM is used by leading practices and academic institutes all over the world. So needless to say, we are truly blessed to have him on board with us. Eyal is going to speak for about the next 40 minutes or so. During that time, everyone will be in listen-only mode, but please feel free to send your questions in to the question box. Afterwards, we'll have a brief Q&A and get to as many questions as we can. We will be recording this webinar, and I'll give you guys details on how to access it after the webinar. But having said all that, I think we'll go ahead and turn it over. Eyal, can you hear me?
Yes.
All right, I'm going to switch the screen over to you, and we'll go ahead and get going.
Right. Okay. All right. Is my screen visible now?
Yep, looks good.
All right. Okay. So I'll present ParaCloud Modeler, which is the first product that we developed here at ParaCloud. What was the real motivation behind it was the fact that we noticed the growing interest in generative design. And while working at architectural firms like Foster and Partners, I could see that it creates quite a bottleneck when you see the expertise required to operate such systems. And I was looking for methods to create generative design systems that doesn't require any kind of scripting. The first product, ParaCloud Modeler, was based on Excel, and it was funny enough to think of Excel as the common denominator in our CAD industry, because most architects were using Excel, and while they were using different kinds of design tools, and they all could actually figure out ways to exchange information numerically in a very precise and easy way without going to bother through formats and so on. So we started developing Modeler. The first beta version was working actually with MicroStation, and then we moved to Rhino. So what I'll show you now is an overview of ParaCloud Modeler. What you see here on the screen is actually an Excel session. Excel runs on the background, and ParaCloud Modeler is developed on top of Excel. What it allows us to do is a way to interact directly with our design in Rhino. So I'm using this ParaCloud CAD driver to connect to my CAD session, which in this case is Rhino 4. I could also integrate it to export to Maya using mail format. I could export DXF files. I could use STL imports, and of course use OBJ files as well in order to interact with other packages, not using just necessarily Rhino. So, but the main tool that we use Modeler for is Rhino, and at the last part of this webinar, I'll discuss GEM, which is our latest product, which is a subset of Modeler and allows you to interact with additional software packages. So Rhino 4 is what we select here. I have a running session of Rhino here at the background, and I've drawn a surface on that session. Now, when I select a surface, and any surface I generate and I rebuild to a situation where the surface is not trimmed without using this retrim option, it actually allows me to get this selection directly into Modeler, and get this information using the UV settings of the surface. So once we have a selection and we import that design geometry, we get the surface brought into our modular software. Now what we can do is start creating matrices in Excel that will allow us to use this piece of geometry and further develop it. So the first, I think, basic feature of the software is component population. So it allows me to take any cell of this geometry and proliferate components on top of that. I'll go to Rhino now and create my two components. This is the first component system called cellular components. So I'm creating just two pieces of geometry. Let's say one will be based on a circle, the other will be based on a rectangular shape, like this. I'm going to extrude those into solids, and using caps and just giving it a starting value. And I take this geometry, the cylinder, and I'm going to name it C. And I'm going to take this and name this thing, let's say, B. So I have a box and a cylinder, and I would like to proliferate those on my geometry. So I'll move back to modular, and I'm going to activate the component system. What it gives us is another layer of the design matrix. This layer is the cellular components, where we could highlight the zone where each cell in this Excel spreadsheet represents a cell in our geometry. Now I can proliferate it with a pattern of components. For example, using B and C in an alternating pattern like this, and laying it out on the surface. This is a representation of the order of the components. Now, if I simply hit Display Cell button, and I'll move to Rhino, you will see that the software started to proliferate, reading the geometry, and it will stretch the geometry to meet the edges of my population cell. Now, we can also control different variables of this component. For example, the depth of the component. So I'll move back to modular, and I'll choose here another layer called Z scale. Again, I can highlight it, and I will just have the boxes, for example, to double the size of the boxes like this. So I lay out a pattern. This represents the depth of the component, and I will use this toggle here to allow the software to calculate using this value. In our session of Rhino, we can clear those components and just simply proliferate it again, hitting the Play Cell button. This will give us a distribution of components around our geometry. So as you can see, this allows us to simply choose components and use a simple stretching and control over the depth of the component using a simple Excel matrix. So this way you could proliferate different kind of components in different methods, and of course you could even relate the population cell to the kind of, let's say, reasoning behind the population. It could be any performative aspect like solar exposure or structural depth and so on. So what we saw here is a very simple population of components, and we saw that we have a matrix that allows us to control what we proliferate on top of our design geometry. Now let's move further on. So we go here back to our Excel session. We have another type of components using what we call the refit corners. And refit corners allows me to create different kind of components. I'm going to use here a surface using a very simple surface using 4 corner points. And what I'll do here, I'm just going to trim this in different sizing. So I'm just going to take here and create different sizing for perforations. Maybe something like this. And I'll copy this a few times. So let's create 5 different components. And what we'll do here, we'll set a trim command to trim those surfaces. So here we're going to use this. So we're just going to use the components in a just trim that again. So I'm selecting the trim curves. Just allowing it to have a growing ratio like this. And when I'm ready, I want to start the trimming process, trimming the center pieces out. Like this. And now when we're ready, we can name these components. So I'm going to call this one 11, and maybe start with a growing naming convention system like this. So the next one could be 12. This one will be 13. This one will be 14. And the last one here will be 15. So we have the different components from 15 all the way through to 11. So I'm going to create another piece of geometry, maybe create a doubly curved surface here. So let's do that by creating a new surface. So I'm going to create this surface based on a section that runs here, maybe something like this. And I'm going to take this surface from this point here like this, and maybe something like this here. And using sweep 2 in Rhino, we can get a doubly curved surface really quickly. I'm going to take this geometry and rebuild it. So I define effectively the grid on top of that geometry. And I'm going to sample it into Modeler. I'm going to start a new session in Modeler. Bring this surface in. And this time what I want to do is use a solar calculator to give me the solar exposure of those panels. Now, having this information, I could document it again to an Excel matrix. And as you can see here, it gives me values for each and every panel. I can take these values and I can rescale them between 11 and 15 and scale this data. So I'm setting the data I wish to scale. I got these values, and I can simply take this, copy it, and put it into my population metrics. So by pasting it here, just copy it and paste it here. So this is just simply the size of my font. I'm just going to slightly shrink it down so you can see. So this is my population of components, and I'm going to use refit corners as a method here. Now, doing so, you will notice that when I place the cell this time, you can see what happens in Rhino. The cells are being stretched and fitted to the doubly curved surface. So it actually panels the surface. Just simply hide this geometry so you can see how the stitching operation works. So effectively what happens is that the software will choose the panel according to the performative value on the surface, and it will choose the right component, and it will match it to the design geometry of our surface. So this is just a quick overview of this first component system called cellular components. We have another component system in modular called ParaCell, which allows us to do a bit more complex operations. And effectively what we will be able to do is to take and write components that are built as NURBs, as cylinders, as lines, as anything we want, and we can actually write it to the level of every point of the component and even use driving parameters to drive the behavior of these components. So once we got a geometry in, and you saw that we could actually proliferate it with components, we could interact with it in many ways, we could create different kinds of operations on top of that. But I think the interesting part is that we could actually interfere with the design process as well. It means that we can control the way that we generate the geometry, and we can either write our own pieces of geometry using a behavior modeling system, or we could take this and interfere with, or actually recreate this piece of geometry. So let's see what we can do with it. We have imported a piece of geometry here. Once the geometry is brought into the software, what you can see here is a list of coordinates noted as A, B, and C. So that's each column represented as an axis of our axis system. If we paint it, what we'll see here is this is a profile of my geometry, and of course there are additional profiles on this geometry. And you can see it's painted here, showing us in different colors each and every profile. Now, if I take this geometry, I could actually control how it evolves. I will use the formation DNA, which is part of our behavior modeling system. Again, it will open an Excel spreadsheet. It will hook the geometry by profile, allowing me to get every profile of my geometry, and each profile gets a column of its own, and I could assign different parameters to control how it behaves. Now, at the D column, we have a behavior toggle, and this toggle is set to 1, which will open all degrees of freedom, 0 will block, or I could actually edit different types of degrees of freedom to block different behaviors. I will set everything now to be 1, so all degrees of freedom are actually allowed. And if you visualize that, you will see that now it's represented in green. So what I'll do here, I'm going to use a rotation about the z-axis. The z-axis is, let's do actually on the x-axis. We'll do rotations about the column A, which is the x-axis of our geometry. And what we need for that is to set rotation angle for the x parameter. So I'm going to use two values. The first profile, I want it to stay in place. The second profile, I want it to rotate, let's say, by 10 degrees. And then I'm going to inherit that throughout the shape. The axis pivot will be set to the first point here at the bottom. So while selecting this point, I can get the point data and set this point to proliferate it through the whole shape. And once applying this deformation, you'll notice that the geometry will start to revolve. So every other profile spins. When I have this change written to my geometry, I can narrate it back to Rhino from the paneling system here using either a NURB surface. By clicking on NURBs, you get the NURBs geometry to be written here. Let's flip that color so you will see that. So you could actually control the different well, we actually, if you think about it, we're driving the geometry by manipulating the different points of the control polygon. And it could be a very complex control polygon, but still we have a very precise control over it. We could take this, we can take this geometry, and of course I could either bring back the geometry, the initial geometry. So if we take it, select it here, all we need to do is simply bring it back in. And if we wanted to do a different kind of behavior on top of that, for example, if we wanted to simply take and do a translation on the z-axis, for example, we'll do that, and we'll do that for every second point of our design geometry. So what I'll do is I'll set it here to be 2 values, and I'll do it in a wavy form, let's say by 5 units. So 5 in and 5 out, but I will allow that only for every second point of my profile. So effectively what I've done now is setting that like this. So those points will stay fixed while this will be shifted. So doing something like this will allow me to activate the deformation and to see how it actually works. So I could do manipulation to the shape, and at any given point, of course, write it as NURBS or as a set of panels, and I could see how this thing is being visualized. So you can see that basically I could control the way that the form evolves. Now, once we have the geometry in, we can also control the way that it behaves as a rib system by providing an offset to it. So I'm going to provide an offset of 1 unit just to see as a starting point how it works. So you can see that my geometry was now converted to a rib system. The rib system starts from the first point here and projected outwards normal to the surface. And of course it creates a set of ribs that we can use for either unfolding and taking this geometry like this. So I go to my rib system, and I could decide that I wanted to build this rib system as a physical model, and I wanted to generate now shop drawings for that. So I'll put a spacing between the ribs that I wish to unfold. I can specify the thickness of my material for notching and set the notching to be automatically created. And doing that by pressing this ribs option, the U rib will now take the U direction of my geometry. You can see it here drawn on my surface, and I want to have this unfolded, so I'm going to set this to unfold and use the U ribs again, and you can see that the software now generated an unfolded view of those ribs. It numbers the ribs as well. So what we end up with is a nice set of drawing, shop drawing, that can go directly for laser cutting, and we can do the same for the second direction, the U direction. Sorry, this was the U, so the V direction, and get this unfolded properly, cut out, and of course assembled very simply. You could get the numbers etched on your ribs as well. Now, we could develop different kinds of panels on top of that and control this geometry. And again, once we have a piece of geometry in, every element or every parameter of this geometry is exposed to us. So we could again use this matrix interface to work with it. So what I'll do here, I'll take the offset and document it into a matrix. This is the matrix that represents it. So if you think about it, if I would go to change this sizing like this, and just use Excel to copy and paste formulas here, I created this as a control mechanism for the ribs. And when I bring this back to read it to the ribs, you will notice that now my ribs changes their dimensions. So I could control each and every point of my design normal to the surface and therefore control its offset. And of course, this allows me to develop different kinds of component system if I wanted to. Now, let's see what we can do with this piece of geometry. And let's use the reference side, which is the outer side of our design geometry, to create some components on top of that. So what we can do is take this geometry now. We can go to Rhino, and instead of creating the components in Rhino like we used before in the cellular component, create the components in Rhino, import just the names. This time we're going to really create the geometry of the components within ParaCloud. And we're going to use the ParaCell system, which is opened from our component system. I'm going to use a simple component. A component is defined within a bounding box. The bounding box represents whatever happens between a cell of our piece of geometry. And of course, we can generate it and draw it in Rhino and sample it in. So I'm using the active component and building an empty component to Rhino. This generates a sampling cube. The sampling cube that you can see here is located at the 0, 0 like this. And it shows us how it will match the geometry of our surface. So the positive points are on the surface while the negative points are on the reference plane. What I'll do here is draw simple lines that will be converted into cylinders. So I'm going to use a line from here in this diagonal and a line on the other diagonal like this. And then I'm going to use one line here to connect to our main geometry. So if I delete the box, we got these two lines here, which I'm selecting now, going back to modular, and I'm importing those into the ParaCell component system. Then I'll move to the second component, simply by going to the second component, selecting the other diagonal, and importing that in. So we have a notation system that allows us to define this component. We can preview this active component and see how it looks either as a cylinder. So we can see how it resides on the first population cell. And we can control here the radius of that cylinder. So let's say that we wanted to have this bit that connects to the surface very small, so we'll move this to 0.1. And we wanted the main diagonal to be, let's say, 0.3. And I'm going to use on the other diagonal 0.3 as well. Now, if I preview this geometry, only this time, in my population matrix, I'm going to use two components. I've got component 1 and 2 in an alternated way. And I can lay it out on my geometry. It will automatically calculate where it needs to go. And I'll use the population matrix and preview that as cylinders. So we get a system. You can see the studs that were defined as thinner cylinders and the outer system that goes here. And of course, when building it, it will build directly to Rhino. So we can see how that goes. The geometry is now rebuilt itself on our Rhino surface, following the rules of our components. I'm going to hide the surface so you can see what we created. Let's just get rid of all these other parts here. Now let's say that we want to control this in a little bit more interesting way. Let's say that we wanted the frame system here, the outer frame, to change its thickness based on the height of our geometry. So when we go higher, I want it to be with thinner geometry. So what I'll do is I will set up parameters that could actually control that element. And these are driving parameters. So I'm going to set a driving parameter here for the first component, and I'll do the same for the second component. The driving parameter starts after the last point. And what I'll do is I'll use the thickness of this. I'm going to set this parameter 1 to be the thickness, 0.3, setting it now, and here again, 0.3. And simply comparing this value to parameter 1, so it reads from the first parameter. And this is simple Excel linking that we can do. So if we change this value here, we can even take this and nest this thing to this value here. So changing this value here to, let's say, 0.2, and preview that will change our design geometry. If we want it to be very thick, we can change it to 1, so you'll see the big difference, and so on. Now, I want you to chain this, but read different values for this parameter. So we have our parameters matrix. For each and every cell where we populate a component, we have up to 9 different parameters we can use. This is parameter 1, 2, 3, 4, 5, 6, up to 9. So we take parameter 1, and we need to read some values into it. What I'll do is I'll document the height of my geometry. Every point of my geometry can be documented to a matrix. So this gives me a simple view of the height matrix of my geometry. And this is documented as a numeric matrix here. Now I can take this geometry and I can rescale it, saying that when it's the bottom will be 1 and at the top it will be 0.1, and I will use 1 decimal place for accuracy and select these values, and I'm going to scale this data. So this is now scaled. Here there is a real number behind it, so you can see the real value. Let me just change the font so you can easily see that. Just use a thinner, let's make it 7. Okay. So now you can see the real values here. Now by selecting the value for parameter 1, I could simply get the data in, and this is aligned properly for the process of applying it to my design. So I'm going to preview that. It's going to read the value, write those here to the viewer so you can see how it drives the size of the component. And we could get that. And when we're happy with the result, we can simply build it here and replace this piece of geometry. So we can get this out. And we can press the build button, go to Rhino, and you can see that it builds the geometry in Rhino. And we got a simple way to control the different parameters of our geometry and components without writing a line of code, but actually simply using Excel matrices and linking information that could this is just a very, I think, quick overview of what we can do. We can go and build more complex components, and for training purposes, we have on our website. Just show you that we have a website that basically deals with tutorials of our products. If you go to our community website, it's called ParaClouding.com, and it's accessible from ParaCloud.com, of course. What you see here is sets of tutorials that you have here in the support section. So you have for Modeler both PDF tutorials and video tutorials. Any tutorial you choose, you can view it here and of course follow it and know how to use it with the software. Those tutorials are of course here in different categories. It's very simple to use. I'll just do a quick overview of GEM, which is the second product that we've got, and explain a little bit about the difference between the two. GEM is a product that we wrote from scratch. We actually started with the concept of modeler, but we were looking even to simplify it one step further. So instead of using Excel as our interface, we decided to use a more graphical approach. So what GEM is doing, it's actually using meshes instead of surfaces. It allows us to sample geometry from mesh files. So both our design geometry and our components are made of meshes. And we can use that, that geometry brought into GEM from Rhino, for example, or Sketchup, or any tool that supports Collada, OBJ, DXF, and STL. And we can work with this very simply and very fast, and get this thing done as a population system or a generative design system in a very fast way. Let me just start the software here quickly. I just need to set something up. 1 second, bear with me. Okay, I can just start it up. So GEM is a standalone tool. It works alongside our CAD. When you open the software, what you get here is a component view where you could populate with mesh components. When you take geometries in GEM, what you do is you select your geometry. I'll use the same surface that we had here before, only this time we need to rebuild it to degree 1. So it will get faceted. We can generate a mesh from that. And we need to export this mesh geometry to a wavefront file. So I'm going to call this thing, let's say T1 wavefront. And I wrote this information in. When I load it, I can navigate to my file, bring it in. Let me see, I took it from a different folder. Let me just do the export again. Okay, I overwrote in this file, so now I'll load it. Okay, we've got the mesh geometry in. This time we can manage the offsets simply by creating visual offsets. We can control different kinds of offsets, for example, by height, and set it to be at the base thicker than the top, for example. So we can do lots of manipulations on that. And of course, any components you proliferate on that will respond to this cell. Now, when we have the geometry brought in, we can choose different components, again, brought from Rhino, but I'll use this example very quickly. So you have our geometry. We have the outer side, which is in red, and the inner side in blue, and we can decide on different sizing for this geometry. So I'm setting the offset to 1 unit. And what I'll do here, I'll just work on the reference on the red side, and I'll proliferate different values based on points of interest. So I could easily select where I want my values to be higher or smaller, whatever I decide. Choose those points of interest, and when I choose a command, for example, like shrinking these red faces, I could control how it responds to those points of interest. So when it's close to this point, I want it to be big, and when it gets further away, I want it to get smaller. And doing that, you will notice that, of course, now you can see the visual effect of that. When I preview that with components, So you can see that effectively I've created this kind of an iris system that responds to points of interest. Now, when I create an output from that, I can create the output in different formats, from DXF to Collada, STL, VRML, whatever I want, and bring that geometry by simply importing that in, calling the file I just created, and of course the geometry will be brought in. So I can find simple methods to control geometry this way, and there are many tools that we can work using random tools, directional tools, all kinds of effects that we wish to create on patterns, as well as controlling the different patterns of our design geometry. Just to show a quick view of something like that, what I'll do here is I'll go to GEM and I'll go back to our original surface. So let me reload the geometry, set the offset, the initial offset to 1, and then I could randomize that offset, for example. And when I randomize the offset, I'll just use an offset, let's say random, between, let's say, 1 and 4. And then I could level this offset to the minimum values, which will now give me frames in different random thicknesses, like this. And if I wanted to control something, I could have various components populated on that geometry, again using this concept of alternating between components. So we have a way to create a quick checkerboard system, and we can use this checkerboard to proliferate different components. We can use up to 10 different components based on colors. So instead of specifying names or numbers, we'll specify colors. And what I'll do here, I'll just quickly create a simple leg component. So let's say I'm going to use a quick draft here of a system like this. Take this geometry, extrude it upwards as a solid, of course. We can take this, we can export that geometry to a component. We use OBJ again, so I'm going to call this thing leg 1, and I can proliferate that. We got that component created. We bring it into the first component. I can rotate it like this so it sits within the face. I'll bring the same component here, only rotate it differently. So effectively, it will give me the second direction. So I've got the red component and the orange component. When I populate using the face population map, I can get a system like this created. And of course, you can do more and more of these systems very quickly and very fast in GEM. So what this system is allowing me to do is create simple components and graphically array those, control our meshes, control the design geometry. We can even go to a level of changing the whole mesh system. For example, if you subdivide the geometry and alternate between the different colors, you will notice that my design geometry can be now converted to a different system. For example, I would like to use a pattern around these diagonal shapes. So what I'll do is I'll take just the orange color and rotate it, which will later allow me to join those faces together around these matching edges. While joining those together, I created a new mesh system that is an offspring of my original geometry. And now, if I will checkerboard this, we can see how it looks. And of course, if we change and use the same leg system that we had before, it will behave differently based on the new geometry. So we can do different kinds of things, or we can simply use a frame component and just use the new system we just created. So anything we do it can be then brought to Rhino as another alternative, which will be very easy to create and control. We have an animation system, a sequencer that will allow us to record commands and play those in an editable mode. And all that elements are very easy to use in a very friendly interface. Again, for learning this software, you can find a demo version of GEM on our website. Let me just go to so if you go to paracloud.com, you have the download GEM option. You can download the software here, and in the tutorials section you'll find tutorials for GEM, which you can follow up and see what is possible to do with the software in a very simple and easy way. Every video tutorial here is about 15 minutes or so. I think that's quite a run through the two packages. So we can wrap it here, and I will be more than happy to take your questions and try to answer those.
Okay, so it looks like the only question right now is it's about SketchUp.
Yes.
Camilo wants to know if you can try it in SketchUp. I don't think we have time to do that, but I mean...
Yes, well, for SketchUp we have GEM that integrates really nicely with SketchUp because we use Collada format. I'll just do a very quick, just to show that. If I open SketchUp, it means that you can even work with the free version of SketchUp with GEM and use the Collada format. With SketchUp Pro, you can use OBJ, so there's no problem with that. But if you take SketchUp and you take a piece of geometry from SketchUp, let's say I'm creating this piece of geometry here, just extruding it quickly like this. I'll select this face and I'll export it to Collada. So let's use a 3D model export. We use Collada format, and I'm triangulating the whole thing here. I can decide if I want to triangulate or not. What it does, it will create a Collada file that we can read into GEM. So in GEM we go to load our mesh, and we load from Collada format and take this file here. I'm using a metric format, and I can then join these together like this, and we can see that we got the geometry in. We have a profiler tool that will assist us with getting the geometry to point to the right direction, which we can later on start using subdivision tools, for example, like this. And I'll give it a quick offset. Maybe 1 meter is too much, so I'll use minus, let's say, 0.2. It will go outwards. I can weld this geometry as well. And what I'll do here, I'll just do a quick checkerboard so you can see. I'll use my 2 components to proliferate the 2 leg components I created. And I will export that, and I'll use Collada output as well. So I'm creating a Collada output, which will allow me to then bring it into SketchUp by importing that Collada output. So you can see that I could get the geometry to read and write, and simply take this, and of course I can even clean it up a little bit using the smoothing option. Yeah, so that's basically a very simple way to interact with SketchUp here.
Okay, great. And then here's another question. Aviva says, I'm glad you made GEM because using Excel is confusing. Are all the surfaces created closed, valid poly surfaces? Are they ready to send and print, or will there need to be other steps to make them ready to print?
Okay, so for 3D printing we have lots of tools in GEM, and the key concept to that is if you create a watertight component, then the proliferated result will be ready for printing, so there shouldn't be any problem with that. So always my advice is to make sure that your components are 3D printable. We have lots of ways to control 3D printing outputs. One thing we have for 3D printing, is the ability to take the components into the fabrication plane, and you can assemble those together. So if you take each individual component, like what we've got here, and you don't want to print it in one go because it will take quite a lot of time to 3D print a large model like this, you can take these elements to the fabrication plane. So we could create an unfolded layout and just create and define spacing between the components. For example, I use 0.6 maybe here, and I'm generating here an unfolded view of my components, which will allow me to get those ready for generating a quick 3D print and then assemble those. We have an assembly markers that we prepare with those as well in the DXF output. But the key, I think the key answer here is that once every component is watertight, so the result is a mesh, and if you generate it as STL output directly from GEM, it should print quite all right. We tested with Z-Corp, with Objet Machines, with SolidDo, with I think with EOS as well. I'm not sure. I can check that out with Dimension, lots of machines. And also for jewelry design, we tested with some wax printers, and it works pretty nice.
Okay, so looks like that's all the questions we had. I'm going to go ahead and switch it back to my screen, and we'll wrap things up here. Okay, great. So I just want to thank you, Eyal, and I want to thank everyone. I mean, that was really, truly fascinating. I want to thank everyone again for joining us for this presentation of Novedge's Best of the Best webinar series. Just in case you're unfamiliar with Novedge, we're the leading online design superstore. Not only do we have the best prices around, but our staff is incredibly awesome and extremely knowledgeable. You can call and chat with us at any time. Everyone who attended this webinar is actually going to get a $100 coupon off the list price for ParaCloud Modeler. We'll be sending out an email with that coupon sometime tomorrow, so just hang tight. We'll get it to you as soon as possible. I'd also like to draw your attention to another bit of info that's a benefit to you. Here at Novedge, we look to go above and beyond for the design community. We've created several communities to foster the collaboration and communication between design professionals. One such community, Rhino Jungle, as you can see on your screen, is would be something of interest to all of you guys using ParaCloud or even GEM. If you're not already a member, it's free, it's easy to use. When you sign up, you get instant access to all the latest information, trends, news, videos, tutorials. This webinar will actually be made available on there. I want to emphasize too, it's not just about Rhino. I mean, we have a lot of members who use ParaCloud, so you can like collaborate with them and network. Basically, it's all things 3D modeling. So join if you get a chance. Having said all that, if you have any other questions or concerns, I'd love to hear them. My email is right there on the screen, Vince@Novedge. Please don't hesitate to email me. I'd love to hear from you guys, any input you guys have on the webinar. Our next webinar in 2 weeks will be on After Effects and Cinema 4D, so stay tuned for that. Having said all that, Eyal, is there anything else you want to add real quick?
No, I think I hope that everything was clear, and of course if anyone has any question about either Modeler or GEM, they can contact me as well to info@paracloud.com through the website, and we'll be more than happy to assist with any question about the software. And you're probably going to find GEM as well available through Novedge in the coming I guess we'll try to set it up as soon as possible.
Yeah.
So we'll be able to maybe offer a discount to this group as well on GEM.
Yep.
I'll be happy.
So yeah, I mean, again, thank you, Eyal, and thank all of you for attending. Until next time, we'll see you then.
Well, thanks a lot, everyone.
Bye-bye.